All right, this is question 1. The diagram shows the graph of the curve y equals x plus 1, x minus 1, and x minus 2. Use the graph to solve the inequality where the curve is less than 1. Okay, so it says use the graph. So we're going to apply a graphical method here. So I'm going to draw the line y is equal to 1, which is that line there. And essentially, we are asking the question, where is this graph less than 1? So it's going to be this part of the graph, and it's going to be that part of the graph, right? So let's just highlight that very quickly. So we're interested in this part of the graph and that part of the graph. Okay, so what x values give us that? Well, we want to find out whatever x value this is. Okay, so we can like go down like that and read off that x value, and it's going to be everything to the left of that. And we want to find out what this x value is. Okay, and this x value there, and it's going to be everything in between. Now, it's rather difficult for me to read off those values on the screen that I've got, but I've checked the mark scheme, and they say that this value here is negative 0.8, this value here is 0.55, and this one here is 2.25. So in effect, what we want is we want x to be less than negative 0.8, and we want x to be between 0.55 and 2.25. So hopefully as you do it on your sheet of paper, right, you should be able to see that as you draw the line down, you do get those values. Okay. All right, then question 2, the function f is defined by f of x is equal to 1 minus 4x minus x squared. Write f of x in this form, which is the completed square form. Okay, well, let's just do that. So I'm going to write f of x here, and I'm going to rearrange the order a little bit as negative x squared minus 4x plus 1. And the first thing you always want to do with this is to factorize out the coefficient before the x squared. So in this case, that is just negative 1. So I can factorize that out and get x squared plus 4x. And we can leave the constant term alone, right? Because we're only going to be completing the square with the terms with the x's in it, right? So the x squared term and the x term. So we can just leave that guy out. Okay, so how do we complete the square with this? Well, we always look at the coefficient of the x, which in this case is 4, and we divide it by 2, right? So if I divide 4 by 2, I'm going to get 2. And then we write x plus 2 squared minus 2 squared. Okay, so if you're wondering what's happened there, just do it nice and slow. We take that 4, we divide it by 2, and then we do x plus 2 squared minus the 2 squared. And the reason we do that is because this is going to be equal to all of that, right? And you can check it by expanding it out if you wish. Okay, so then what's this going to simplify to? We're going to get negative bracket x plus 2 all squared minus 4 plus 1, which is negative x plus 2 squared plus 4 plus 1, right? So there I've just expanded the bracket with the negative 1. And so this becomes 5 minus x plus 2 all squared. Okay, and that's in the form that we want, right? Where a is equal to 5 and b is equal to 2. Okay, so that's all good. All right, part B, we want to find the range of this function. Well, I think the best thing to do is just to sketch the function. Now, why do we do the completed square form? We do the completed square form like this because it tells us the location of the vertex. So if we've got the curve, right, y is equal to x minus a squared plus b, what that means is that the vertex is at the coordinates a and b. Okay, so what I mean by the vertex, right, is on the quadratic graph, like that or like that. Oh, sorry, that's a bit bad. Like that, right? The vertex is this point here, right? It's the minimum or it's the maximum. And so the completed square form tells us where that point is. So in this particular case, right, what's happened? Well, we've got x minus minus 2. Right, so the vertex is going to be at negative 2 for the x coordinate, and it's going to be at positive 5 for the y coordinate. Okay, so I can read off here that the vertex is going to be at negative 2, comma 5. So if I was then to try to sketch this out, right, so here's my graph. Okay, so 1, 2, so that's negative 2, 1, 2, 3, 4, 5. right? So the vertex is going to be there. Now, what else do we know about this quadratic? Well, it's a negative x squared, isn't it, right? This is a negative quadratic. So instead of it being a happy face graph like that, so that's a positive x squared, it's going to be a sad face graph like that, which is the negative x squared. Okay, so we're going to have a quadratic which is going to be sad face. And, you know, if I was to draw it, it kind of looks something like that. And something like that. Okay, the y-intercept should be 1. So we can kind of draw like that. Now then, if I do this, it's very clear what the range is, because what do we mean by domain and range? Domain, right, is the set of all possible input values, right? So the domain is the set of all x values that can be taken into the function, right? It's the inputs. And what's the range? It's the set of all y values, right? It's the outputs. So we can see from this particular graph, right, that f can take any value of x as an input. That's totally fine. But what are the outputs? Well, it can only get up to 5, and it can't go beyond that, right? There's no value of the output which is greater than 5, because 5 is the maximum. So the range for this function is going to be f is less than or equal to 5. Okay? So the domain is all the real numbers. Okay, but the range can only be the numbers which are less than 5. Okay then, so the function g is defined by the same thing basically, but with the different domain that x is greater than k, where k is a constant. State the least possible value of k such that g has an inverse. Now, okay, I've done a really long video on this on the channel, going through domain, range, inverse, all that kind of stuff. But let's recap it very briefly. What is an inverse function? Right, its job is to undo the action of the original function. Now, what do I mean by that? Imagine that we had an input into the function, and that input is the number 3. And that gives us an output, and the output is, oh, let's say 4. So what's the job of the inverse function? The job of the inverse function is to take that output 4 as a new input and to give us back 3 as the output, right? So if the function f takes in 3 and gives out 4, the inverse function is supposed to undo what f has done. In other words, if it takes in 4, it should give us back 3. That's its job. Okay. Now then, this connects with the idea of one-to-one, many-to-one, and one-to-many mappings. So let's try to discuss what those are. So what's a one-to-one mapping? Oh, one-to-one. Okay, a one-to-one mapping is where you've got one input corresponds to one and only one output. So the classic example of that is just going to be a straight line, right? If I've got a straight line, okay, every single input corresponds to one and only one output. Okay, so that's one-to-one. What about one-to-many? Let's do many-to-one first, many-to-one. Okay, well, an example of many-to-one would be a quadratic graph, like y is equal to x squared. Because what it means is that there are many possible inputs that could give you the same output. So draw a quadratic like that. Let's make that y is equal to x squared. So what are we saying? Imagine that we've got x is 2, right? That gives us the output of 4. But we could have also got the output of 4 with the input of -2, right? In other words, there are many inputs, in this case 2 inputs, which can give us the same output. So this is a many-to-one mapping. And lastly, we have got a one-to-many, right? So a one-to-many is, we could think of it as x is equal to y squared, if you prefer. One to many. Okay. And so we could have a curve that looks like that, or the square root of x if you prefer. And in this particular case, we've got one input which gives us many outputs. So let's say the input is 9. What's the output that we could get? We could get 3, or we could get -3, right? So one input gives us many possible outputs. Now the key thing, the key fact that you need to know is that the first two, these guys, right, one-to-one and many-to-one, these are functions. These are totally fine. This guy here, a one-to-many, is not a function by definition. And you can sort of think about it and say, just practically speaking, right, we don't want to have the situation, for example, like in a computer system, where one input could have two equally possible outputs, right? That's going to create all sorts of problems because, like, well, what output should we choose? Okay, so we don't want to have this situation here. So, so this is a no-no. Now, how does this connect with what we've said before, right? The job of a function is to undo the action of, a job of an inverse function is to undo the action of an original function. Well, if we've got a one-to-one mapping, right? So one input to one output. If we were to invert it, right, then we're going to get a one-to-one again, right? Because the one output becomes one input, and one input becomes one output, right? So in other words, these two guys here, they switch. So a one-to-one will invert to give a one-to-one. A many-to-one, however, will invert to give a one-to-many, right? Because those guys switch, inputs and outputs switch. So then, if I've got a many-to-one mapping, if I was to invert it, I would get a one-to-many, and a one-to-many is not a function, right? That is not a function. So in other words, this guy is a function, right? So is a function, but you cannot invert. Right, so we cannot invert this guy. So the only functions that we can invert are one-to-one functions. Okay, so that's basically the reason. Okay, so we want to state the least possible value of k such that g has got no inverse. Okay, so we go back to our graph, right? So we always draw the graph because, you know, if you're not drawing the graph, it's crazy. You can't understand it. This guy is a one-to-one. This guy is a sorry, I just got a call come in. This guy is a many-to-one. Okay, so this cannot be a function. So instead what we need to do is we need to change this into a one-to-one. Well, how could we do that? Well, we could cut it in half. If I was to cut it in half, right, I can get rid of everything on the left and just be left with the stuff on the right. And if I do that, this guy is now a one-to-one mapping. And because it's a one-to-one, it means that it can be inverted. Right, so I'm going to go over here and say, okay, so if I make sure that k is greater than or equal to, whatever it was, -2, okay, so in other words, k is equal to -2, then g is one-to-one, and it can be inverted, therefore. Okay? All right, I'm just going to pause there. All right, then, so using your value of k, find g inverse, stating its domain and range. All right, so what is an inverse function, right? Again, it is this diagram. We are reversing the inputs and outputs, right? So if we now were to think about it, okay, we put in an input, which is x, we get an output y. What's the job of the inverse function? To take that output y and to take us back to the original input x. So if I've got my function, which was y is equal to whatever it was, 5 minus, what was it? 5 minus x plus 2 squared. Basically what I want to do is want to rearrange that and make x the subject. Why? Because here I've got my output in terms of my inputs. So I want to rearrange it to get the input x in terms of the output y. So the way I can do that is I can get x plus 2 all squared is equal to 5 minus y. I can square root both sides. So I get x plus 2 is equal to plus or minus the square root of 5 minus y. And so we get x is equal to -2 plus or minus the square root of 5 minus y. And it is convention that we write the inverse function such that the input is rewritten as an x, right? So I just take the y and I replace it with an x. Now then, this whole thing, is it a plus or is it a minus the square root? Well, we're not sure yet, but what we're going to do is we're going to think about the domain and the range in order to answer that question. So if we go back over here, right, we thought about the domain and the range of the function g. So let's try to think about it now. We are going to get the domain and the range of the function g and the function g inverse. Okay, so the domain of our function we've just said is x is greater than or equal to -2. Greater than or equal to, I think it was. Yeah. And the range is y is less than or equal to 5. Now, let's have a quick think about it, right? If we're talking about the inverse function, then if we go back to this diagram, right, if all of my inputs to the original function was, let's say, we just use what we got here. So x is greater than -2, and the outputs are all the y's which are less than or equal to 5, right? So this is like the domain of f, and this, or g in this case, and this is the range of g. Okay, so these are all the possible outputs of g, right? So those are going to become the inputs to the inverse function, right? So the range of the original function is going to become the domain of the inverse function, right? Because the outputs become the inputs. So what's the domain of this inverse function? Well, it's got to be the same set of values. So in other words, we're going to have x is less than or equal to 5, right? Because all the values that are less than or equal to 5 come out of f, so they've got to go back into the inverse function. And what outputs should we expect from the inverse function? Well, we should expect them to be the same as the inputs to the original function. So in other words, our outputs should be everything that's greater than or equal to -2. So that would be the range of the inverse function. So in other words, the domain of the inverse function is going to be the same as the range of the original function, and the range of the inverse function is going to be the same as the domain, right? Because that's the job of the inverse function. So we can go over here and say, all right, so our domain for the inverse function is going to be x is less than or equal to 5. And our range is going to be y is greater than or equal to -2. Okay, so now I can go over here. Say, all right, where was it? So my domain for this is x is, what was it? Less than or equal to 5. And the range of g inverse, sorry, I should call it g, it's g inverse, is x is greater than or equal to -2. Okay, so that's what we get for the domain and the range. Now that's going to help us to understand whether or not we're going to have a plus or a minus here. Right, because we're saying that our output values need to be greater than -2. So here I've got -2. Well, then I can't subtract from that, right? Because then I'm going to be lower than -2. So instead, what I've got to do is I've got to add. So actually, in the end, this is not plus or minus, right? This is just plus, because the range is everything that's greater than -2. Okay, all right then. Now, do I have to sketch this? I think I did. Let's see if there's the next part of this question. Okay, no, well, we were not asked to sketch the graph, but I think it's probably going to be a useful thing as well. So we just have a quick look at what that's going to look like. So I'm going to go back over here, like that. Okay, so this is now our function g, isn't it? All right, so that's our function g. Okay, so let's get rid of that. Get rid of that. So that there now is g. Okay, so what's our inverse function going to look like? Well, it's going to be the square root graph. Okay, and we also know that the inverse functions are reflections of the original. So reflections in the line y is equal to x. So if I was to draw a line y is equal to x, like this, our inverse function is going to be a reflection of that. So what does that mean? It means most importantly, that this point gets reflected, doesn't it? So instead of being at the coordinate of -2, 5, we're now going to be at the coordinate 5, -2. So that's going to be like here, right? Here's -2. Right, so that coordinate goes there. That's 5, -2. Okay, and this point as well, right, would also be reflected in this point here. Okay, so it's kind of a slightly bad drawing that I did. But we had a y-intercept at 1, so we would also have an x-intercept at 1. And so then the shape of the graph would look something like that. Okay, so that would be the graph of the inverse function, right? That is a square root graph that has been reflected basically kind of like in the y-axis. So usual square root graph looks like that. But if you've got a negative inside the square root, it goes like that. Okay, so if you were wondering what the graph looks like, and you may be asked in the future to sketch a graph like that, then that's what it would look like. And how do I get it? Well, I consider the original graph, the original function, and I think of it as a reflection of the line y equals x. And I can also think about the domain and range, right? We'd said earlier that the domain and range of the inverse function is x is less than or equal to 5, right? That's what we said. And y is greater than or equal to -2. And that matches up perfectly. Okay, I hope that was all helpful. Okay, question 3. We want to show that 2 tan theta plus sec theta times 2 tan theta minus sec theta is equal to this thing here. Well, okay, we're just going to expand the brackets on the left-hand side. So 2 tan theta times 2 tan theta is 4 tan squared theta. And then we're going to have 2 tan theta times by minus sec theta. So that's minus 2 tan theta sec theta. And then we'll have sec theta times by 2 tan theta. So that's plus 2 tan theta sec theta. And then we've got sec theta times by minus sec theta, which is minus sec squared theta. Okay, so this is the left-hand side, isn't it? So LHS is equal to that. Okay, well, we can see that these two terms cancel each other out. And so we are left with 4 tan squared theta minus sec squared theta. And then we can use the identity which is given to us in the front of the exam. And the identity is that sec squared theta is equal to 1 plus tan squared theta. Okay, and so we just substitute that in. So we end up with 4 tan squared theta minus 1 plus tan squared theta. And that gives you 3 tan squared theta minus 1, which is what we're asked to show. Okay, so part B, hence solve this equation is equal to 1. Well, that means, isn't it, that we're solving 3 tan squared theta minus 1 is equal to 1. Right, that's what the word hence means. We've got to use the result from the previous question. And so rearranging that, tan squared theta is going to be equal to 2/3. And so therefore tan theta is the square root of that, which is plus or minus the square root of 2/3. Now, how are we going to solve an equation like this? There are different ways we can solve trigonometric equations. Sometimes we use the unit circle, sometimes we use the graph, and in this case, I'm going to use the graph, right? So I'm going to graph out y is equal to tan theta, okay? And I'm going to use that to find out when tan theta is equal to plus or minus root 2/3. So how do we plot the graph of tan theta? The key thing to know is that we have asymptotes at plus and minus 90 degrees. Okay, so we've got an asymptote at -90 and at +90. Like that. And the tan wave looks something like this. And the second tan wave, right? Because the tan wave repeats every 180 degrees. So we've got another tan wave, which is just the same thing, which is going to look like that. Okay, so the key thing about the tan wave is it has those asymptotes of plus and minus 90, and that the period of the tan wave is equal to 180. So if we want to solve where tan theta is equal to plus or minus root 2/3, then basically we're trying to find out when does this graph intersect the line plus root 2/3 and also minus root 2/3. Okay, and we can use the calculator to find out the first of these values. So we'll find out that value there. So we do the tan inverse of positive root 2/3, and that gives us, I think, 39.2, right? So that value there is 39.2. And hopefully by symmetry, you can see that that value there would have to be the same value but negative, right? So we get negative 39.2 degrees, right? So what's going on there? Essentially, we're using the property that tan of negative theta is equal to negative tan theta, right? So in other words, if I was to find the tan of 39.2, I get this value here, right? Positive root 2/3. Well, because of sort of symmetry, the negative of that value, the negative 39.2, if I find the tan of that, it's basically the same value, but negative going down. Okay, so I end up with these two values here. And essentially what I want to do is want to say, okay, well, do I know this value? And do I know this value? And yes, I do, because this value here is equivalent to this one, but it's just one wave along. So I've moved one wave to the right. So if I move one wave to the right, that means I've got to add 180 degrees because one wave period is 180. And the same thing with this guy, I move 180 degrees to the right. Okay, so I want to get solutions, right, which are between 0 and 180, right? So in other words, that's 180 there. So I want to get these two solutions. Okay, so the first solution we know, right, theta is equal to 39.2. But the second solution is going to be negative 39.2 plus 180, and that's going to be 140.8. So those will be the two solutions there to my equation. Okay, question 4. The diagram shows a design for a logo. The logo is a sector of a circle with radius of r and angle of alpha. The area of the logo is 9 centimeters squared. Show that the perimeter is given by this. Okay. Guys, with a circular measure question, there are only really two formulas that you need to know. The area of the sector is a half r squared theta, and the arc length of the arc length is equal to r times theta. But the key is both of those angles must be in radians. All right. Okay, so if we're told that the area is equal to 9 centimeters squared, then we know that 9 is equal to a half r squared times by alpha. And so therefore we know that 18 is equal to r squared alpha. Okay, so we got that. How do we get the perimeter? Well, the perimeter is going to be these two lengths here. So that length and that length. So two lots of r plus the arc length. So we're going to have 2r plus r theta. Or rather r alpha in this case, right? Because alpha is the angle. Well, if we use this relationship here, right, we know that we could rearrange this such that alpha is equal to 18 upon r squared. So if I just substitute that into here, I've got 2r plus r times by 18 upon r squared, which is equal to 2r plus 18 upon r. Okay, so we've done that for part A. Part B, given that r can vary, find the stationary value and determine its nature. Okay, well, we know that p is equal to 2r plus 18 upon r. So I'm going to write that as plus 18r to the negative 1. So if I differentiate this, right, if I find dp dr, then that's going to give me 2 minus 18r to the power of negative 2. And we'll differentiate it again because we want to determine the nature of our stationary point. So this will become positive 36 r to the power of negative 3. Now, when do we get a stationary point? We get a stationary point when dp dr is equal to 0. Okay, that's the definition of a stationary value. So we want to find where 0 is equal to 2 minus 18r to the negative 2, or 18 divided by r to the power of 2. So if I rearrange that, 18 is, or 18 upon r squared is equal to 2. And that means that r squared is going to be equal to 9, which means that r is equal to plus or minus 3. But of course, we can only have the positive value. So we've now got r is equal to 3. So that's the stationary value of r. We want to find the value of p of that. So when r is equal to 3, what is p? P is going to equal to 2 times by 3 plus 18 divided by 3. And that's equal to 6 plus, sorry, 18 divided by 3. 6 plus 6, beg your pardon, which is 12. Okay. And then we want to substitute it into the second derivative to determine the nature. So d2p dr squared is equal to 36 upon 3 cubed. It doesn't really matter what value that is. The key thing is that it is a positive number. And since it is positive, therefore we have a minimum value at r is equal to 3. and p is equal to 12, right? So that's the key thing. The second derivative is used to determine whether or not we've got a maximum or a minimum. If the second derivative is negative, we have a maximum. If it's positive, we have a minimum. Okay, then question 5. The tangent to this curve here at the point where x is equal to 3 meets the line y equals x minus 16 at the point A. Find the coordinates A. Okay, well, let's try to think through this question. We've got a tangent. How do we find the tangent? The tangent is just the equation of a line. So how do we find the equation of any line? We need a coordinate point, and we need the gradient of the line, right? So this is the key thing to understand, right? The tangent is just a straight line. How do I find the equation of any straight line? I need a point, and I need the gradient. So let's take those two things in turn. How do I find the coordinate point? Well, I've got the x coordinate is 3. So the y coordinate is going to be found by substituting into here. So let's just do that. When x is equal to 3, y is going to be equal to the square root of 3 plus 1, which is 4, divided by 3. So 3 plus 1 is 4, square rooted is 2, so y is equal to 2/3. Okay, so we've got our coordinate point now. The point is 3, 2/3. So that's done. How are we going to get the gradient? Well, to get the gradient of the tangent, we need to differentiate this curve. Okay, and how are we going to differentiate that? Well, we've got one function divided by another function. So when we've got one function divided by another function, we have to use the quotient rule because we have the quotient of two functions. And we are going to call the function on the numerator u and the function on the denominator v. So let's just write that down. U is equal to the square root of x plus 1. So it's x plus 1 to the power of a half. And v is equal to x. And if we know our quotient rule, the quotient rule is going to be v du dx minus u dv dx all over v squared. Okay, so what I need to do is I need to find out what u du dx is and what dv dx is. Okay, so I need to differentiate this. So if I differentiate this, it's a chain rule. So I'm going to take the power, bring it to the front, and subtract 1 from the power. So I kind of differentiate the big bracket first. I then look inside the bracket at x plus 1. I differentiate that, which will give me 1, and I multiply by that. So just recap. A chain rule is when we've got one function, like x plus 1, inside of another function. So how do we do that? We differentiate the function on the outside first. So the half comes down to the front, reduce the power by 1. And then after that, we look at the function on the inside, we differentiate it, and we multiply through by that. If we differentiate v, right, no, differentiate x, we just get 1. So that's fairly straightforward. Now let's try to now substitute everything in. So we have got x times by a half x plus 1 to the power of minus a half minus u, which is x plus 1 to the power of a half, times by dv, which is 1. And that's all over v squared, so it's all upon x squared. Now then, we're not actually asked to simplify this, but I think it's a good thing to do. If we wanted to simplify, essentially, we are looking for the terms on the numerator, which are fractions. And that's that thing there, the half. And it's also this thing, because this is power of a negative. So when we've got a negative, we've got a reciprocal. So this thing here literally means, right, 1 divided by x plus 1 to the power of a half. Or if you prefer, it means 1 over the square root of x plus 1. So those are like fraction terms there, right? The half and the x plus 1 to the power of negative half. So how can I get rid of those fractions? Well, I just have to multiply through, right, by x plus 1 to the power of positive a half. Because if I did that, if I multiply by x plus 1 to the power of positive half, then this term here is going to disappear. It's going to cancel out. Okay? So we got rid of this kind of fractional term. And to get rid of the half, right, I can multiply by 2. So that means that if I do that on the top, I also need to do that on the bottom in order to maintain an equivalent fraction. Okay, so as I said, you're not required to do this in this question, but I think it's good because some questions ask you to do it. So I just want to do that with you. Okay, so now if I multiply this by this, the half cancels off with the 2, and this term cancels off with that term. So I'm just left with x. If I multiplied this by this, right, then the x plus 1 to the power of a half times by x plus 1 to the power of a half, these powers add up. Right, so I've got a half plus a half, which is 1. So I end up with x plus 1 to the power of 1. And of course, I've still got the 2, right? That 2, so I multiply through by that. And on the bottom, this thing becomes 2x squared, x plus 1 to the power of a half. Okay, so now I think I can simplify this. So I've got x minus 2x, that's negative x, minus 1 over 2x squared, the square root of x plus 1. Okay, so just done that for the benefit of those of you who want a bit of help practicing how to simplify expressions, because you are asked to do that. Now, what was the point of us differentiating this? We wanted to find the gradient, right? The gradient of the tangent at the point where x is 3. So now we've got to find when x is equal to 3. So when x is equal to 3, y prime is equal to minus 3 minus 1 over 2 times by 3 squared, so 2 times by 9 times by the square root of 3 plus 1. Okay, well, on the top we got negative 4. On the bottom we got 2 times 9 times by 3 plus 1 is 4, square rooted is 2. Right, so this looks to me like we've got a gradient of... oh, hang on, have I done that wrong? Oh, that's minus 2 there. Sorry, because I did this earlier. That's minus 2. That's minus 2. Yeah, I seem to remember it was different. So this thing here is negative 5. Do beg your pardon. Sorry about that. Negative 5. And so this thing is going to become, oh, what is that? Negative 5 upon 36. Okay. All right. By the way, just, I mean, it's tempting, isn't it? If I make a mistake, I can stop it and I go back and re-record it. But I want to point out something just about your exams. It is so easy to make small mistakes, right? So when you do your exam, a good thing to do is once you've done everything, right, and hopefully you've got about half an hour, 20 minutes left, ask for sheets of paper, blank paper, and just go over and do the question again from scratch. Because as you read through your work, it's very hard for you to spot where you've made an error. But if you do it again, first thing, then you can compare and see if you've got the right answer or the same answer, sorry. And I think that's a good error correction mechanism. Okay, so this thing here, the gradient we've now got is negative 5.36. Okay, so we can now find the equation of the tangent. And the way we're going to do that, right, the equation of the tangent is y minus y1 is equal to mx minus x1, where m is the gradient and x1, y1 is the coordinate point. So I've got y minus, what was it, 2/3 is equal to m, negative 5 upon 36, times by x minus x1, which was 3. Okay, so that's the equation of the tangent. So we've done that, which is most of the work. Now, we are told in the question that this tangent meets the line y equals x minus 16 at the point A. Find the coordinates of A. So in other words, we want to find the intersection point of our tangent with this line. So we're going to be solving simultaneous equations. Well, the easiest thing to do then is just to set the y to be equal to x minus 16, right? We just substitute in. So that's what I'm going to do. So I'm going to say x minus 16 minus 2/3 is equal to minus 5 upon 36, x minus 3. Okay, now guys, I think at this point, best thing to do, get rid of the fractions. So we're going to multiply everything by 36. Okay, so I'm going to write here 36 bracket x minus 16 minus, okay, so if I multiply by 36, we got 2 times by 36 over 3. I'll write it like that for the moment. And then this is minus 5 x minus 3. Okay, now simplifying the fraction, I can divide top and bottom by 3, so that becomes 12. So here what I've got is I have got 36x minus 36 times by 16, which I don't know what it is yet, minus 2 times by 12, which is 24, is equal to minus 5x plus 15. So I'm going to add 5x to both sides and bring all the x's to this side. I'm going to bring everything else to the other side. So that's going to give me here 41x, and then I'm going to have 15 plus 24 plus 36 times by 16. All right, okay. I don't have a calculator with me, so that's going to be kind of annoying. That's 39. Oh, plus 36 times by 16. Oh, man, I should probably just do that over here. 36 times by 16. Okay, 6 times by 6 is 36. And then 6 times by 3 is 18. So that's going to be there, 21. 0 here, 10, 1 times by 6 is 6. 1 times that is that. So I get that to be 6, 7, 5, 5, 7, 6. And so if I add that on, that's going to be 606, 615, I think. Yep. So 41x is equal to 615. So x is going to be 615 divided by 41. Well, I did the answer earlier, so I think I'm going to cheat a little bit if you don't mind. So x is 15. You can do the long division as well. I mean, you got to prepare for not having calculators, guys. So I guess that's, that's just part and parcel. So let's just do it over here. 615 divided by 41. How many 41s go into 61? 1. What are the 41 there? Subtract off. Yeah, hang on, wait. Oh, it's been so long since I've done this. So that'd be 205, is it? Okay, and then, yeah, okay, then how many 41s go into 205? That is 5. Okay, yeah, does work. All right, then, so we got x is equal to 15. I think we want to find the y value as well. So y is equal to x minus 16. So we got 15 minus 16. So we get -1. So the coordinate of A is going to be the point 15, comma, -1. All right, so there's a lot of work there, guys. It's quite hard, right? So what's the key thing I suggest you do? You want to think about finding the equation of tangents as break it down into finding the coordinate point, finding the gradient, and just pushing through like that. Okay, it's a lot of work, but I think if you're patient and you're methodical, it should be all right. All right, question 6, we want to find the integral of this. So first of all, we're going to write it in indices form as 3x plus 2 to the power of -1/2, right? The negative is the reciprocal, means 1 divided by, and the half is the square root. Okay, so how do we integrate a term of this form? Well, we add 1 to the power and divide by the new power. So that's going to be 3x plus 2 to the power of +1/2 divided by +1/2, which is the same as timesing by 2. And then what do we do? Well, we look inside the bracket. 3x plus 2, we take the coefficient of x, which is 3, and we divide by 3. Okay, so we get that term there. So if you're a little bit uncertain, essentially you just got to know the rule, right? If I've got ax plus b to the power of n dx, then the way I integrate that is I add 1 to the power. So I get a power of n plus 1. I divide by the new power, so I divide by n plus 1. And I also need to divide by the coefficient of x, which is a. So that's the general rule. And you can think about it this way, right? If you imagine differentiating this, right, then you should get back to that, which is what happens, right? You could differentiate this, bring the power down to the front. So n plus 1 would cancel with this n plus 1. And then you'd have to differentiate the ax plus b, which gives you an a. You'd multiply by a, and that would cancel out with that term there, right? So you are hopefully be able to reason that out. Part B. Okay, so we want to find this integral in terms of a. Okay, so if we integrate e to the power of 1 minus 2x dx between 1/2 and a. So if we integrate the exponential remains the same, but we need to divide by the coefficient of x, and the coefficient of x here is -2. So we're going to divide by -2. So the same thing as timesing by -1/2. And then we're going to substitute in the upper and the lower bounds. So if I substitute in the upper bound, I'm going to get -1/2 e to the power of 1 minus 2a. And then if I substitute in the lower bound, I'm going to get -1/2 e to the power of 1 minus 1, right? Because 1/2 times 2 is just 1. So that's going to be -1/2 e to the power of 1 minus 2a minus -1/2, so it's +1/2 e to the power of 0. And of course, e to the power of 0 is just equal to 1. So what we end up here is 1/2 minus a half e to the power of 1 minus 2a, or if you prefer, 1 minus e to the power of 1 minus 2a, all divided by 2. Okay, so I'm just going to check the mark scheme, see if that's all okay, but I'm fairly confident it is. So let's just have a look at that. Yeah, that's all fine. Right, question 7, which is slightly more unusual binomial expansion question. So we've got in the expansion of x plus x squared to the power of 8 in ascending powers of x, the third and the sixth terms are equal, find the value of x. Okay, well, if this is in ascending powers of x, then that means that the powers of x have got to get bigger and bigger and bigger. So that means that if we're doing the expansion, so we've got x plus x squared, these terms here, the x terms need to get smaller, and these x squared terms need to get bigger as the progression goes on in order for the overall term to be increasing. So we're going to have an x to the power 8, x to the power 7, x to the power 6, right? X to the power 5, x to the power 4, x to the power 3, x to the power 2, x to the power 1, and x to the power 0. So I'm writing this all out in full just to make a point, okay? And then we've got x squared to the power 0, x squared to the power 1, x squared to the power 2, x squared to the power 3, x squared to the power 4, x squared to the power 5, x squared to the power 6, x squared to the power 7, power of 7, and then that one will be x squared to the power of 8. And then, of course, we've got the coefficients, right? And the coefficients of, sorry, this is the power 8, isn't it? The coefficient would be like 8c0, 8c1, 8c2, and so on and so on and so on, right? So 8c2, 8c3, so on and so on. Now, the key thing is, right, when it says the third term, I think a lot of people are going to say, it's got to be where this thing is power 3, but it's not. If you're really careful, right, this is the first term, this is the second term, and this is the third term where we've got power of 2 here, right? So that guy is the third term. And why is that? Well, because we start, don't we? Not at 1, but we start at 0, right? So x squared to the power 0 is the first term, and x squared to the power 1 is the second term, okay? So we want this term here, and we also want the sixth term, right? So 4, 5, 6. This will be the sixth term, and the coefficient of that there is going to be 8c5. Okay, so we're saying that those two terms there are equal. Sorry, I haven't bothered to write out the coefficients for those, so I hope you get the point. So the reason I wrote it all out is to make it very, very clear to you that this is the third and this is the sixth. Okay, okay then, so let's write this out. We are told that 8c2 x to the power 6 times by x squared squared is equal to 8c5 x to the power 3 x squared to the power of 5. So if we were now to expand on this, right, 8c2 is 8 factorial over 2 factorial 6 factorial, right? That's the formula or the expression that's given to you in the front of the exam for 8c2. This is x to the power 6, and x squared squared is x to the power 4. 8c5 is 8 factorial over 5 factorial 3 factorial, and we've got x to the power 3 there, and x squared to the power 5 is x to the power 10. Okay, now I think we can simplify this a little bit. The first thing we can do is we can divide both sides by 8 factorial. So that's gone and that's gone. The next thing we can do is we can combine up the powers of x. So we've got 1 upon 2 factorial 6 factorial, beg your pardon, times by x to the power 10, because we add the powers, 6 plus 4. And this is 1 upon 5 factorial 3 factorial, and times by x to the power 13, right? Because we add up the 3 and the 10. Okay, well, let's move the x's all to one side. And what that means is we're going to divide both sides by x to the power 10, right? So I'll divide both sides by x to the power 10, like that, x to the power 10, and x to the power 10. So if I do that on the left-hand side, it's just going to cancel. On the right-hand side, I'm going to get the powers subtract. So x to the power 13, and I've got a minus the 10, so I get x to the power 3. So I get here 1, I get 1 upon 2 factorial 6 factorial is equal to 1 upon 5 factorial 3 factorial times by x cubed. Okay then, so how can I simplify this one? I'm going to multiply both sides by 5 factorial 3 factorial. So 5 factorial 3 factorial over 2 factorial 6 factorial is equal to x cubed. And hopefully you know that if I've got 5 factorial divided by 6 factorial, I'm just going to be left with a 6 on the denominator. Now, just try to think about that. What is 6 factorial? It is 6 times 5 times 4 times 3 times 2 times 1, isn't it? So actually, that's the same thing as 6 times by 5 factorial. Yeah, because the 5 factorial is these remaining terms here. So I can choose to write the expression on the left as 5 factorial times by 3 factorial over 2 factorial times by 6 times by 5 factorial. Okay, so the 5 factorials cancel off. Gone and gone. And so on the top, I've got, on the remainder, I've got 3 factorial divided by 2 factorial times by 6 factorial. Well, 3 factorial is just equal to 6, so that cancels as well. So I end up with x cubed is equal to 1 upon 2. So x is equal to the cube root of a half. Cube root of a half. Okay, so I think that was the right answer, but I have to kind of go away and check that against the mark scheme. Let me just do that very fast. Where are we? Okay, so we want... yeah, they write it as the cube root of 28 upon 56, which is really weird because 28 upon 56 is just a half. So that's pretty strange. But my answer is correct. Okay. All right. So next one. In the expansion of x plus 2 upon x to the power of n in decreasing powers of x, the sixth term is a constant. Find the value of the positive integer n. Okay. Well, just think about it again, and I think we'll write out the full expansion as I did before so that we don't make a big mistake. So 2 upon x to the power of n. So we want decreasing powers of x, so that means that the powers of this term have got to be going down as this one's going to be going up. So we're going to have x to the power of n times by 2 upon x to the power of 0, right, times by nc0 and so on. And the next term is going to be x to the power of n minus 1 times by 2 upon x to the power of 1 times by n c1 and so on and so on and so on, right? So remember, this is the first term, this is the second term, right? So what's the sixth term going to be? Well, the sixth term is going to be nc5, right? Because we've got to subtract 1. X to the power of n minus 5, 2 upon x to the power of 5. Right, so the key thing for you to understand is that, right, just as this is the first term and this is 0 and that's 0, and this is the second term and that's 1 and that's 1, for the sixth term, right, we need a 5 here and a 5 here. Okay, so that's like the key thing. So we've got the sixth term. And we are told that this guy is a constant. Well, let's just try to write that down fully. So nc5 means n factorial over 5 factorial n minus 5 factorial. This is x to the power of n minus 5. That's going to be 2 to the power of 5 over x to the power of 5. Now, if this is going to be a constant term, what does it mean about these two x's? Right, what does it mean about that guy there and that guy there? Well, they're going to have to cancel out. So how are they going to cancel out? Well, they're only going to cancel out if the powers here are the same. So we can basically say, if this is constant, then we require that x to the power n minus 5 must be equal to x to the power 5, which is the same thing as saying that n minus 5 is equal to 5, so the powers must be the same. So n is equal to 10. Okay, so we get a value of n is equal to 10. So that's done the first part. Second part is actually just finding the value of the sixth term. Well, look, we just then substitute into here. So just move across to the right. So n is now 10, right? So we get 10 factorial over 5 factorial, 5 factorial. Those x's cancel out, right? Because we've got x to the power of 5 2 to the power of 5 over x to the power of 5, right? So as we said, that cancels, that cancels. So now we just got to simplify this. So 10 factorial, right, is 10 times 9 times 8 times 7 times 6 times by 5 factorial, over 5 factorial times by 5 factorial times by 2 to the power of 5. Okay, well, one of those 5 factorials can cancel off. That's gone and that's gone. And again, we'll try to simplify this. So 10 times 9 times 8 times 7 times 6 over 5 times 4 times 3 times 2 times by 2 to the power of 5. All right, well, what's the best way of cancelling this? I guess 3 and 2 is 6, isn't it? So that's gone. We can divide the 8 by 4. That gives us 2. We can divide the 10 by 5. That gives us 2. So we end up with 9 times 7 times by 2 times 2 times by 2 to the power of 5, which is going to be 2 to the power of 7. So we have got 63 times by 2 to the power of 7. And what's 2 to the power of 7? 2, 4, 8, 16, 32, 64, 128. I'm counting it on my fingers, by the way, doubling each time. And okay, so we would have to do this. I mean, I'm guessing that they would allow you to use a calculator for this kind of thing, but I'm working on the basis that you're not going to have calculators. So let's just do the long multiplication. 3 times by 8 is 24, isn't it? And then 3 times by 2 is 6, so that's going to be 8. 3 times by 1 is 3, okay? Put a 0 there. 6 times by 8 is 48. 6 times by 2 is 12, so that's going to be 16. 6 times by 1 is 6, so that's going to be 7. Ooh, so 4, 16, 9, 10, 8. So I get 8064. So I'm hoping that goes right. And just check the mark scheme. 8064 is the right answer. Okay, now I know, guys, I'm going a little bit overkill, isn't it? We're doing all of this by hand, but I know that, starting from 2025, isn't it? You don't have calculators for paper 1, I think. So you need to also be trying to work through improving your mental arithmetic and your basic ability with numbers. So I think if you can, you want to try to do as much of the paper without a calculator and just be stretching those muscles as well, which is why I'm doing it a little bit more with you. Okay. Okay, so question 8, we want to solve the equation sine 4x is equal to a half. That means that 4x is going to be equal to the sine inverse of a half. And the sine inverse of a half is pi by 6. But of course, there's another solution at 5 pi by 6. And we know that because sine of x is equal to sine of pi minus x by using the property of the symmetry of the sine wave. Okay. So then if we divide both sides by 4, we're going to get pi by 24 and 5 pi by 24. Okay. Now, if you're really not sure about the thing that I've just said about the symmetry, I'll just try to draw it out for you, right? So imagine we've got the sine wave like this. So here's the sine wave, something like that. Okay. So there's the sine wave. And this is pi, that's 0. Here is pi by 2. So imagine if I've got a point, and we're going to call that point, I don't know, x. Then this would be sine x. Well, that's going to be identical to this point over here, right? Because we've got a line of symmetry at pi by 2. So if you think about it, if the point 0 is symmetrical with the point pi, and this point x, right, which is the distance of x away from 0, is also going to have a distance of x away from pi. So that coordinate there is going to be pi minus x, right? That's kind of the logic of that. Okay, so part B. Diagram shows parts of the graph of y is equal to sine 4x and y is equal to a half. Find the exact area of the shaded region enclosed by the curve and the line. All right, then. Well, firstly, we know that the intersection is going to be pi by 24, isn't it? And 5 pi by 24. And so how can we find the area of this region? Well, I guess what we could do is we could integrate underneath the curve between pi by 24 and 5 pi by 24, which would give us that whole region there. And then we could subtract off the area of the rectangle. That is one way of doing it. The other way is to say, okay, we've got a region which is defined by a boundary on the top and a boundary on the bottom. Okay, so if we actually want to find the area of the region, we could say the area is equal to the integral of the function on the top, which is sine 4x, minus the function on the bottom, which is a half, integrated with respect to x between the boundaries of pi by 24 and 5 pi by 24. Okay, so if we integrate sine 4x, we are going to get negative cos 4x divided by 4, so negative 1 upon 4 cos x. If we integrate negative a half, we get negative a half x. And so we are now going to put in the boundaries of 5 pi upon 24 and pi upon 24. So if we did that, we would get here negative a quarter cos of 5 pi upon 6 minus 5 pi upon 48. Okay, and then minus, if I substitute in the lower boundary, negative a quarter cos pi by 6 minus pi by 48. Okay, so what I want to do is I want to substitute this into my calculator. So if I type in cos 5 pi by 6, I think I get negative root 3 upon 2. So it's going to be negative a quarter times by negative root 3 upon 2. Minus 5 pi upon 48, minus minus, which is plus a quarter, and cos pi by 6 is root 3 upon 2, and then minus minus, which is plus pi upon 48. So this is going to give me positive root 3 upon 8, plus root 3 upon 8, minus 5 pi upon 48 plus pi upon 48, which is minus 4 pi upon 48. So root 3 upon 8 plus root 3 upon 8 is 2 root 3 upon 8, which is root 3 upon 4, and then minus pi upon 12. So I get as my final answer there root 3 upon 4 minus pi upon 12. And I'm going to check the mark scheme, see if that's all okay. So let's just go down. Hang on, wait. Yeah, that looks okay. Okay, question 9. We want to write this thing here in the form of p plus q root 10. Okay, so I think what I'm going to do is I'm going to start by combining these terms into one fraction, which means I need to give this one the same denominator as 2 plus root 10. So I'm going to rewrite this as 16 plus 11 root 10 over 2 plus root 10 is equal to 2 plus, is equal to, beg your pardon, plus 2 plus root 10 over 2 plus root 10, right? So I've rewritten the 1, right, like that. Now if I add the two numerators together, I've got 16 plus 2, which is 18, plus 12 root 10 over 2 plus root 10. Now you need to simplify early and often. That is a really key thing for add maths. And on the top, I can simplify that by factorizing out the 6. So that's exactly what I'm going to do. 3 plus 2 root 10 there. One of the key issues I found is that students do not simplify it, and then they end up having like these massive numbers and everything gets really, really complicated. Okay, so if you can simplify, you want to simplify. Okay, so now what do I want to do? I want to rationalize, and the way I rationalize is I multiply by the conjugate, and the conjugate here is 2 minus root 10. Okay, so if I've got 2 plus root 10, the conjugate is 2 minus, and the reason we do that is because when we multiply these two things together, the square roots are going to end up cancelling off. So on the top, what have I got? I'm going to multiply out those brackets. So 3 times by 2 is 6. 3 times by negative root 10 is negative 3 root 10. 2 root 10 times by 2 is plus 4 root 10. And then 2 root 10 times by negative root 10, so we're going to get negative 2. Root 10 times root 10 is just 10. And then I'm going to divide through by, so let's do the denominator now. 2 times by 2 is 4. 2 times by minus root 10 is minus 2 root 10. Plus root 10 times by 2, which is plus 2 root 10. And then root 10 times by minus root 10 is minus 10. Okay, so let's simplify. So we've got 6 bracket. So we've got here 6 minus 20 by the looks of it. And 6 minus 20 is equal to negative 14. And we've got negative 3 root 10 plus 4 root 10. So that's positive root 10. All over 4 minus 10 is negative 6. And the negative 2 root 10 plus the 2 root 10 just cancels off. And so that's a happy coincidence for us because it means also the 6 is cancelled off. Junk, junk. And so we've got negative 1 on the bottom. So we just multiply top and bottom by negative 1. And that's going to give us 14 minus root 10. Okay, so I think that's going to be the answer. And I'm just going to check it against the mark scheme. So let's just find that. 14 minus root 10 is the answer. Right, question 10. Suzma is training for a marathon. In the first week, she runs 10 kilometers. Then each week, she runs a distance that is 10% greater than the week before. The total distance that Suzma has run by the end of n whole weeks is more than 200 kilometers. Find the smallest possible value of n. All right. This is a geometric progression, right? It's a little bit more disguised than it is in other questions, but it is a geometric progression. Why? Well, because if you start with 10 kilometers, right, and then you increase by 10%, what that really means is you're timesing by 1.1, right? So to go from here to increase by 10%, right, is the same thing as having a common ratio of 1.1. That's what it means. Okay, so to go from one term to the next term is going to be like that, right? So So we have got a geometric progression where the first term is equal to 10 and the common ratio is equal to 1.1. So we want to find the total distance that she's run by the end of n whole weeks. Okay, so we want to find the sum of the first n terms, basically, because first week she runs like 10, then the next week she runs 11. So add those two up, you get 21, and so on and so forth. So the sum of the n terms is equal to a bracket 1 minus r to the power of n over 1 minus r. And actually, that's the same thing as a r to the n minus 1 over r minus 1. So we're going to substitute values in. So our a is equal to 10. R, as we said, is 1.1 to the power of n minus 1 all over r, which is 1.1 minus 1. Okay, now 1.1 minus 1 is 0.1. And dividing by 0.1 is the same thing as timesing by 10. So this is 100, 1.1 to the power n minus 1. So we want to find out where this thing is greater than 200 kilometers. Okay, so we want to find out when 100, 1.1 to the power n minus 1 is greater than 200 kilometers. So that's the same thing as 1.1 to the power n minus 1 is greater than 2. The same thing as 1.1 to the power n is greater than 3. Okay, so how can we solve this? Well, we'll treat it as an equality for the sake of argument at this point. And we can use logarithms to do that. So we can say log 1.1 to the power n is equal to log 3. We can then use the log rule to bring this power n down to the front. So we get n times by log of 1.1 is equal to log of 3. So n is equal to log 3 divided by log 1.1. Now, I don't have my calculator with me, so you just give me a second. I think I'll just double check against the mark scheme, if you don't mind. So we just bring it down. Where am I looking? Yeah, so my method is correct. So they give you a term, and presumably you're gonna have to round it. Okay, just give me 1 second, guys. Okay, I've put it into Google and I get 11.52. So I get 11.52. Okay, well, we want to be greater than that, right? So n, because we can't have 11.52 weeks. We can only have integer numbers of weeks. So we want n must be greater than or equal to 12. Okay, and that is the answer. Okay, then part B of this question, we have got a geometric progression has first term a and a common ratio r. the first, second, and third terms of the geometric progression are the first, third, and seventh terms of an arithmetic progression. Find the value of r. Okay, I think we just need to know what the formulas are here for geometric progressions and arithmetic. For a geometric progression, the nth term is equal to a times by r to the power of n minus 1. And for an arithmetic progression, the nth term is equal to a plus n minus 1d. Okay, so where a is the first term, for the case of a geometric progression, r is the common ratio. And for an arithmetic progression, d is the common difference. Okay, now we just need to be a little bit careful here because in our two expressions, right, we're not told that the, oh, we are actually, yeah. The first term of the geometric progression is the same as the first term of the arithmetic progression. So we can just say like the two a's, the two first terms are the same. So I was going to say that if we didn't know that, then we'd have to use a different ladder to distinguish the first term of the geometric progression from the first term of the arithmetic, but we don't have to. So that's okay. So now we can just match it up. The second term of the GP, so the second term is going to be a times r to the power of 1. And that's equal to the third term of the arithmetic progression, which is going to be a plus 2d, right? Because the third term is a plus 2d. And then the third term of the geometric progression, so the third term is a r squared, is equal to the seventh term of the arithmetic progression. So that is a plus 6d. Okay, so essentially we end up with two equations, right? First one is here, and the second one is here. And so what are we going to do? Well, we are going to try to find out what r is. Okay, so what is a way in which we could do this? Well, I think it's tempting for me to rearrange and get everything in terms of d. So for the first equation, I'm going to get d is equal to a r minus a. And for the second equation, sorry, that's 2d. For the second equation, I'm going to get 6d is equal to a r squared minus a. And the reason I've done that, right, is because then if I divide one of these equations by the other, I'm going to eliminate the d, and I'm also going to eliminate the a, and that's quite effective. So I'm going to do the first equation, 2d is equal to a r minus a, and I'm going to divide it by the second, 6d a r squared minus a there. Okay. Okay, so I'm going to cancel off the two d's here. The d is gone, and I'm going to cancel off the a's, right? So divide by a, divide that by a, which gives me a 1, divide that by a, divide by that a, which gives me 1. So I get 2 divided by 6, which is a third, is equal to r minus 1 over r squared minus 1. So I'm going to multiply both sides by r squared minus 1. So I get r squared minus 1 over here. I'm going to multiply both sides by 3. So 3 bracket r minus 1. So I'm going to get r squared minus 1 is equal to 3r minus 3. And that's going to give us r squared minus 3r plus 2 is equal to 0. So r plus, I don't know actually, r minus 2 minus 1, which is probably reasonable. So r minus 2, r minus 1. And so therefore r is either equal to 1 or r is equal to 2. And we were told in the question, isn't it, that the common ratio cannot equal to 1. So that guy is gone. So r is equal to 2 has got to be our answer. So let me just double check that against the mark scheme. Yeah, r is equal to 2. Okay. And that gives you, if you get that, it's extraordinary that they give you all 4 marks. Amazing. If you just write that down, you get all 4 marks. Incredible. Okay. They give you the method on the right-hand side of the mark scheme, but there are effectively no method marks. I'm amazed. Okay. Well, I hope that was helpful, guys. Okay, question 11. There are 3 girls and 2 boys standing in a straight line. Find the number of possible orders of the following cases. No girls are next to each other. Well, let's draw it out. Okay, so 1, 2, 3, 4, 5. Now, if no girls are next to each other, that means the girls have got to go here. Okay, and then the boys will have to go there. So we're trying to arrange 3 girls, which are fixed in these locations. So how many ways can I arrange 3 girls? That's 3 factorial or 3p3. And then I've got to arrange 2 boys. How many ways can I do that? 2 factorial or 2p2. And I want to have the 3 girls and the 2 boys. So I'm multiplying these 2 things together, right? So I've got 3 factorial, which is 6, times by 2 factorial, which is 2. So that's going to give me 12. Okay, then part 2. The 2 boys are not next to each other. Well, let's consider that the other way around. Let's consider the ways in which the boys are next to each other. So we'll imagine the boys there like that as 1 unit. So how many ways can I arrange the 1, 2, 3, 4 units, right? Because I'm now considering the boys as like stuck together as one thing. Well, there are 4 factorial ways of arranging those units. And then how many ways can I arrange the 2 boys? Well, there are 2 ways or 2 factorial ways. So I multiply through by 2 factorial. So I get 4 factorial, which is 4 times 3 times 2 times 1 times by 2, right? So 4 times 3 is 12, times by 2 is 24, times by 2 is 48. And of course, what I want is the boys not to be next to each other, right? So I've got to consider, right, how many ways in which there are no restrictions. So no restrictions is just going to be 5 factorial. In other words, it doesn't matter where the boys and the girls go. And I've got to subtract off the number of ways in which the boys are next to each other, which was our 48. So we've got 5 factorial minus 48. So 5 factorial is 5 times 4 times 3 times 2 times 1 minus 48. So 120 minus 48, which is 72, I believe. Okay, then, so part B, 12 people, including Angie and Bube, are divided into 3 groups of 4 people. Angie and Bube must not be in the same group. Find the number of ways in which the 3 groups can be selected. Okay, well, I think the best thing to do is, again, just draw this out. Here I've got 3 groups, 1, 2, 3, okay? And I'll put Angie in this group and Bube in this group. Now, it really doesn't matter, right, where they go. Angie could go here and Bube could go there. So long as they're not in the same group, that's all that matters. So the order in which I write these 3 groups is completely irrelevant, okay? Because all we're doing is we're dividing into the same into groups. So the order of the groups does not matter. Now, when the order doesn't matter, we are going to use combinations. And that's really pretty much the key thing that you need to know about combinations, permutations. Permutations, the order matters, right? Because we are arranging items. Combinations, order doesn't matter. We are just choosing items. So I want to go through each of these groups and say, well, okay, what do I want? I want 4 people to be in this group. I've already got 1 person, so there are 3 people that I need to choose. And how many people can I choose them from? Well, I started with 12 people, and I've already chosen Angie and Bube, so I've got 10 people left to choose from. So in other words, there are 10 C3 ways that I could fill the remaining slots in this group. Okay, so now what's happened? Well, I'm going to be left with 7 people to choose from, right? Because I had started with 12, I've got Angie and Bube already, so that's 10. I've chosen another 3, so 10 minus 3 is 7. And how many people do I need to choose for this group? Well, I need to choose another 3. So that's going to be 7C3. Again, and once I've done that, I've got 4 people remaining, right? Because I had 7, I've taken 3, so I've got 4 left. And I want to choose 4 to go in the last group, so that's going to be 4C4, right? So I'm going to get that. So I've got 10C3 times by 7C3 times by 4C4. Okay, and I think what we'll do is we'll try to do this using the formula, right? So 10C3 is 10 factorial over 3 factorial, 7 factorial, times by 7C3, which is 7 factorial, over 3 factorial, 4 factorial, times by 4C4, which is just 1. Okay, we can do that, right? It should make sense as well. How many ways can I choose 4 people from 4 people? Well, there's just one way. I just choose all 4 of them. Okay, so I can cancel this out. On top, we get 10 times 9 times 8, because the 7 times 6 times 5 times 4 times 3 times 2 times 1 cancels off, right? The 7 factorial cancels off over 3 factorial. This guy is going to become 7 times 6 times 5, because the 4 factorial cancels off, times by 1. And I think I can probably simplify this, right? So 3 factorial is 6, so that's gone and that's gone. 3 factorial is 6, so I'll write this as 10 times 9 times 8 over 3 times 2 times by 7 times 5. So let's divide through by 3. So that will become a 3. Divide by 2. So that will become a 4. So we end up with 10 times 3 times 4 times 5 times 7, beg your pardon, times by 5. Okay, all right. I don't know what the best way to do that. 3 times 4 is 12. And 12 times by 7 is 84. And then I've got to times through by 5. So how do I times through by 5? Times by 10 divided by 2. So 420, I think. And then times through by 10, 4,200. Okay, so I'm doing it by hand without a calculator because I want to, show you when you're going to do the exam without the calculator. These are some of the tricks you can do for your mental arithmetic. So I hope that that's also helpful. Okay, question 12, which is a kinematics question. A particle moves in a straight line. Its velocity is given by this. Find the acceleration when t is equal to pi by 3. Okay, well, what is acceleration? It is the rate of change of velocity with respect to time, right? So it's given by dv dt. So we just got to differentiate this expression. So if I differentiate cos t, I get negative sine t. And if I differentiate sine t, I get cos t. So I want to find this when t is equal to pi by 4. So when pi by 3, beg your pardon, t is equal to pi by 3, the acceleration is equal to negative sine of pi by 3, which is root 3 upon 2, minus cos of pi by 3, which is a half. Okay, so we get minus root 3 upon 2 minus a half. Part B, the displacement of the particle from the fixed point O is given by S. The particle passes through O when t is equal to 0. Find the displacement at the time when the particle first changes direction. Okay, well, we know that velocity is equal to the rate of change of displacement. That's the definition of velocity. And therefore, if we reverse the differentiation, we're going to get integration. So displacement is going to be the integral of velocity with respect to time, right? Because if I differentiate displacement to get velocity, then it means if I integrate velocity, I will get displacement. So the first thing I want to be doing is I want to be integrating the expression cos t minus sine t. And if I integrate cos t, I will get sine t. And if I integrate negative sine t, I will get cos t. And the reason for that is sine differentiates to give cos, and cos differentiates to give negative sine. And I've got plus c. Well, we are told in the question that the particle passes through the origin when t is equal to 0. So that means that when t is equal to 0, the displacement is equal to 0. And so we can substitute into here, 0 is equal to sine of 0 plus cos of 0 plus c. And sine of 0 is 0, but cos of 0 is 1. And I suspect that will be a mistake that lots of students will make. So c is equal to negative 1. And that therefore means that the displacement can be given by sine t plus cos t minus 1, right? So that's the displacement. Now we're asked to find the displacement at the time when the particle first changes direction. Now, when does a particle change direction? It changes it when the velocity is equal to 0. That's the key fact. So change velocity when v is equal to 0. Now, if you're not sure about that, let's try to think it through. Let's imagine that a particle is moving forward, and after it moves back, right? So this is going forward, and this is going back. So here we've got positive velocity, right? And then as we turn and go in the opposite direction, we're going to have negative velocity, right? Because positive and negative just refer to the direction, right? So positive, you're going to the right, negative, you're going to the left. So what's happened here as you've changed, right? What's going on there? Well, it must be at that point that the velocity is 0, right? Because we've gone from being positive to negative. So we change direction when the velocity is 0. So we know that v is equal to, what's it equal to? V is equal to cos t minus sine t. So we're going to set this equal to 0. which is the same thing as saying that sine t is equal to cos t. And that's the same thing as saying that tan t is equal to 1, right? Because we divide both sides by cos, and sine divided by cos is tan, and cos divided by cos is 1. And we can stick that into our calculator, and we'll get that t is equal to pi by 4, right? So at pi by 4 seconds, the particle changes direction. Okay, so then we just want to find the displacement at pi by 4. So s will be equal to sine of pi by 4 plus cos of pi by 4 minus 1. And sine of pi by 4 is root 2 upon 2. And cos of pi by 4 is root 2 upon 2 minus 1. So that's going to be root 2 minus 1. Okay. All right, then the next one, find an expression for a in terms of s. Well, I think it's just be more clear if we just write down what our a was, right? So our a was negative sine t minus cos t. So negative sine t minus cos t. And I think, why don't we factorize that and write that as negative bracket sine t plus cos t. And then let's write the expression for the velocity, sorry, not for velocity, for displacement, which was sine t plus cos t minus 1. Well, hang on, wait a second. Those two things are the same, aren't they? Right? Sine t plus cos t and sine t plus cos t. So we know that sine t plus cos t is going to be equal to negative a. So I should just be able to write here that s is equal to negative a minus 1. So I think that should be the answer. Now I'm just going to go back and check the mark scheme for that. Make sure that everything is okay. All right, so for the first part, we get negative 1 plus root 3 upon 2. Just check that. Yeah, that's right, same answer. And then for part B, that should be... Ding, 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 ding. Yeah, that's all right. And then for part C, minus S minus 1. Yeah, all correct. Okay. So it's, oh, sorry, one for A in terms of S. Sorry, I misread the question, isn't it? Oh, silly me. So if I just rearrange that, do beg your pardon, guys. So S plus 1 is equal to negative A. So A is equal to minus S minus 1. I'm really, really sorry about that. I should have read the question more carefully. We want to find A in terms of S. Okay, now, if you're finding these papers helpful, please do share them with your friends. I aim to help as many students as I can who are taking ad maths. And please like and please subscribe. It helps the channel to get more views. Okay, take care and good luck with your exams.